Okay, good morning, ladies and gentlemen.
Morning.
I want to apologize for any English mistake about my English, but anyway, also I want to give a special thanks for all the people that is dedicated for maintenance and reliability practice, for taking the chance to come to this international conference in order to gain and share experience. So we're going to talk about this not typical problem and this not common application of ultrasound. Let's begin. Detecting rotor bar problems on AC induction motor by structural airborne mechanical inspection. This is what we are going to be reviewing. So we are going to take special interest on the problem and the diagnostic charts for this kind of problems using vibration and also referring to motor current analysis. Let's begin talking about TLA. TLA and where is ubicated. As you can see, TLA is an LNG gas that is placed on the Mexican coast of the Gulf of Mexico. So this is a picture of our installations. We have the next organizational structure and process. As we can see, this company is a joint venture where Shell is sharing the 50% and Total the 25% and Mitsui the other 25%. So anyway, we are based and we are on the 50% of the procedure from Shell. So the industry is related to oil and gas. It was founded on the 2004 by Shell, Total, and Mitsui. Headquarters are placed on Altamira, Tamaulipas. The key people here is Mr. Carlos Barajas, General Manager. He's Mexican, Lauren Karwaki from France and Canada, and the other key people on the managerial roles. The products we handle is LNG, liquefied natural gas, and we have about 80 employees inside the plant, and this is our website. So let's talk about a little bit about our process. It's very simple. As we can see in this ship, we basically receive, storage, regasify, and send out natural gas. So this natural gas came liquefied from the south of Africa, basically from Nigeria. So in these unloaded arms, we download and store in a liquid phase in these big thermal tanks. So then, by a little process from regasifying, we input by these centrifugal pumps the liquefied gas to the main process for regasification. So regasification takes place adding seawater for increase the phase to gas, and then we have the natural gas. So we send out to the facilities for power generation by Iberdrola, basically. By this way, we cover this little process. Also, we have these facilities and this technical scope. We have berthing basin, including mooring and unloading facilities for LNG carriers with a capacity 70,000. 2 LNG storage tanks, process equipment for vaporization and gas pressurizing, seawater supply system with capacity of 30,000 meters by hour. Send out facilities into Pemex pipeline and Altamira 5. Buildings, culture room, administration buildings, warehouse, and today this is the actual capacity, and we are looking for an expansion, installing a third LNG storage tank. Okay, let's get into the machine. This is the bad actor. The tag is PM1501. P stands for pump and M stands for motor. So this is an electric motor of approximately 450 HPs and runs about 1,800 RPMs. Is coupled to a double suction bipartite horizontal centrifugal pump, whose function is to provide water for firefighting. The machine operates every week, about 10 minutes, and the road is inspected every 2 months. As you can see, this system don't take part of the process. So, as I was saying, this system don't take part for the main process, but as we can see, it's for firefighting, and in this kind of plants for handling LNG, this is very, very important. We need to keep this system updated and reliable. So when we make the test of this machine, it's only once a week, and as you can see, it's a little testing. This is the motor, and this is the point 1, 2, 3, and 4. And as you can see, this is the machine. This is the report, and also I describe this kind of report, and I recommend to use it. It came and is adapted from Technical Associates of Charlotte, and you can also can use on your plants. So you can add condition monitoring issues like a current, voltage, flow, pressure, temperature. And when we made the ultrasound inspection, we detected this issue on the motor. So why is important why is important to talk about ultrasound and talking about these issues? So this problem was detected as first-line technology. We used ultrasound, and we detected this potential failure has related in this PF curve. So then when we decided to confirm the failure, we used the motor current analysis. So that's why it's very important to use the PF curve, talking about safety and reliability, because this machine is for firefighting. The problem: PM ultrasound spectral analysis shows a typical spectrum of rotor bar or loose broken bar problems in the engine. Note the rotor pass frequency about 102.7 key CPMs and up to 4 harmonics, each one with seed bands around 2 by FL. Maybe this kind of information is new for you, and this is a typical spectrum. We are going to compare it with against the vibration charts. For this spectrum shows clearly this first rotor bar frequency, second harmonic, third harmonic, fourth harmonic, and the seed bands. Look at them, and this is very clear. When you analyze this information, it's very important to distinguish between these kind of frequencies. We can pay attention on the sound, but I prefer to make the analysis using this spectral picture. We can hear the sound. So pay attention. I want to listen very carefully. We are going to repeat the sound. I am going to ask if you notice any different. Again. So anyone hear any different?
I hear a little bit of rolling change.
Go and back sound.
At the end here, they're rolling.
Yeah, go and back sound. Yeah, that's right. You can hear good. Basically, this is the main trait of this kind of problems, as we are going to see on the vibration charts, because the magnetic flux, this causes that this motion go and back, and we can hear run. But we don't have the chance to hear more with more intensify, because the test was very short, only had 10 minutes in operation. But as you leave this motor 1 hour, the sound intensifies, and you can hear without ultrasound. You can hear only besides the motor. This is very important. Let's talk about the diagnosis chart. This is a typical chart from Charlotte's, and as we can see the rotor bar problems, we are remarking this kind of spectra. Normally, the normal sign is having or saying 1 R by PF, but as the problem increase or get worsened, you will have 2, 3, or 4, etc. harmonics, also with seed bands around them. Here again, the main thing to diagnose here and give a right severity is look at the number of harmonics and the seed bands. Because either you can have all these frequency smalls, and maybe you think, no, it's not a problem, but you are dealing with a real problem. As you see more and more harmonics, as we see in the last picture. Yes. Okay. More about diagnostic chart. A normal AC motor signature ought to include a rotor bar pressing frequency response. This response takes place when each motor bar passes slide disrupts within the magnetic field, because the electrical currents pass through the stator rotor geometry. An elevated RBPF is created when the rotor bar passes a significant disrupt in these fields, produced when the current path is altered or disordered from broken or cracked bars, loose or defective rotor bar joints, improperly braced rotor bar joints, porous rotor, bar castings, or electrical arcing across the rotor bar to the end-ring interfaces. RBPF, if recognized, has an integer multiple of rotor speed and will usually have seed bands spaced at 2 by electrical line frequency. Here. Rotor eccentricity problems can be indicated by additional less dominant seed bands sets spaced at 1 by RPM. Here is the main thing that we must take in account. How can I guess or suppose that I am dealing with this frequency? Many people ask this. So has the time advanced, you gain more experience. Also in vibration. We have a lot of experience in vibration and we can easily find and relate this, but not if somebody is new in this field. So this is a little good tip to advise. AC motor have from 35 to 96 rotor bars. Any machine, any AC motor. So you can make an estimation. So an FTT spectrum with sufficient frequency range will be necessary for 1 by RPM and 2 by RBPF will be captured by this maximum frequency, 360,000 CPM with 1,600 FT line resolution, and will provide enough resolution to define the 2 by LF side bands. Severity is usually judged by change in rotor RBPF amplitude over time. Amplitude variation with load is common. So when we make the test, also we don't have enough charge, because 10 minutes is not enough to get the line pressurized. But look how anyway, as we use low load, the problem is present, and we guess if we increase the pressure, the fault is very, very worsened. Let's see the failure zone graph. What we have here is the rotor, and we are pointing here the broken rotor bar causing localized heating and noticeable increase in current on adjacent rotor bars. So here again, we can use thermography to identify this problem, but if we don't leave enough time, as we do with these 10 minutes, if we use thermography, we are not going to find it. So we use ultrasound. If we don't use ultrasound, the problems can go unnoticed. Next slide talks about failure effect. When analyzing the post-mortem rotor failure, locate and identify points of black-handed blue overheating areas, and you can check dye penetrant crack. So this is where we can find the broken bars. Diagonal cross-section of an induction motor shows how the copper rotor bars welded to the two end rings from the rotor squirrel cage. Electrical current induced by the stereo field flows through the bar and end rings to the squirrel cage to produce the torque output of the motor. Thus, broken bars prevent current flow, which then degrades motor performance and can lead to motor malfunction. And that's why we hear the go and back sound. We can see here the bars and the magnetic field. The rotor develops a cooler region due to absence of current flow in the broken bar, see in the left on blue. There is no magnetic flux in attraction force around the broken bar, denoted by the yellow arrows. The combined effect is a motor row bow and accompanying imbalance force. In addition, thick air gap opposite to broken bar contributes an additional force which modulates the 1 by RPM imbalance force and at the rate equal to the number of poles times the slide frequency. So what it means, if we let this kind of problem unnoticed, the problem worsens, so it develops a deflection of the shaft. So what causes this? We are finally we are going to use vibration because the rotor bows and expands both lateral tabs and the motor begins to vibrate axially. And also you are going to detect and generate hot spots, and you can then use thermography. But at this level, the motor is next to a catastrophic failure. Let's talk about the technique used to inspect this motor. The inspection technique was used: mechanical inspection of bearings using magnetic module placed closer to the loading of the bearings. A frequency about 25 kHz was settled. The data was saved and downloaded to the DMS spectralizer for follow-up. This type of problem typically generate audible go-back sound, what we talk about. And here you can see where to take the inspections, either with your stethoscopic module or using the magnetic module. Recommendation and diagnostics. Applying the theory of vibration analysis to ultrasound analysis when dealing with problems of rotor bar loose broken in electric motors, their physics is not due to friction or impact. This is very important, and is not settled an F max suitable for capturing high frequencies in the FFT, then can go unnoticed. Their severity is dictated by the amount of harmonics, also has seed bands around them. This is an advantage of ultrasound in mechanical inspection. So for better results, try to apply and combine at least two diagnostic technologies, as we are going to see on the appendix. Finally, results, it was proceeded to prepare the respective report, continuing with routine monitoring. This type of rotor motor problems are usually related to manufacturing quality problems. And given that engine do not operate continually, this development has been slow. But by predictive tasks, this potential failure has intensified, so shall be changed with a spare motor, which is already in stock. We have this motor, and we are going to change it in the next months. Let's see the Appendix A about the motor current analysis. So we have a police on the sun of my plant. So we are integrated in a committee formed by several plants who gives support each plant to others. So we asked to BAS Stereolution for support. They have a Baker Explorer instrument. So they came to the plant to take a practice on this motor and to confirm this kind of problem. So the people from BAF came to visit TLDA, and MCI results performed on these same engines to confirm the problem. Note the warning notice indicating possible failure on rotor bars. Here, this is the first page from the report, and look all the tests carried, and special attention on rotor bar decibels. This is a warning. The rest of the health of the motor is good. Continuing with the spectral, power spectrum graphics showing the rotor bar pass problem, which also is affected in response to the torque. This is the core of the MCA, as we can see here in the rotor bars. We can see the frequency line and this peaks about the 2/FL, the frequency of the poles. So when we make the analysis, we take in count the peak to the left, and we compare this amplitude. And then we go to the chart and give the right severity. So also look at this torque. This torque was to adjusting the valve to discharge. So it gives a kind of cavitation. Also, you can see the phasoral vectors, and the time waveform for voltage and current is okay. And this is the diagnostic and severity table for motor currents used to assess electric AC motor problems from Charlotte. And then we can see this severity. We are placed here because we have the value of 30.80. Then we place here, and overhaul as soon as possible. And we have the diagnostic multiple cracked or broken bar, end rings indicated, also a slip range, problem with the joints, etc. And the evaluation was this column about the index between FL and FP, frequency line, and the pole frequency on decibels. So with this presentation, I finalize the case study. These are the reference, and finally the acknowledgements, and I can be raised at these emails. So if any of you have any questions, please.
You say that because of
Turn on.
you say that because of differential temperature in the rotor will bow it or bend it and cause vibration. You said the vibration would be in the axial direction.
Mm-hmm.
Wouldn't you get more in the radial direction because of the unbalance? I don't know if I understood that.
Okay.
Te lo digo en español. Dice que el motor tiene una vibración porque hay una diferencia de temperatura en el rotor y que tiende a vibrar en la dirección axial. ¿No sería más probable que vibren radialmente por diferencia de peso?
Sí, this is a good question, and is fitting for level 2 vibration analysis. As you can see, we have two main axial problem and two ways to detect that. So if you have your deflection in the middle of the rotor, is going to generate a pure 1/RPM axial vibration also. But if you have the main deflection on any side, in inboard bearing, outboard bearing, you are going to have an uneven bowing. So this is going to cause a 2 dominant RPM, and this is going to be noticeable axially. Yeah, that's right. Any question more?
What UE equipment did you use to originally detect the rotor bar problem? Was it a 10,000?
Yes, we use UltraPro 10,000.
And then what transducer did you use with that?
When I talking about the technique, I was speaking about using the magnetic model, because in the first time we was inspecting this route looking for bearing damage. So we used the magnetic model for easy way to and save more time. But a special tip here for you, I prefer using on any structural inspection the contact model. The ultrasound waves conduce better along the bar. But if you can use them, always there are places where you can, for safety, you can place the contact model. You must place the magnetic model and get back from the risk condition.
And what location on the motor were you monitoring?
¿Qué punto? One, let's see. This is the configuration. As I was talking, this is based following the suggestion from technical associates. You can set your phase point here in the outboard bearing, and then the point number 2 next to the coupling. When you set the vibration frequencies, you use this horizontal point for higher electrical problems, and then you set the number 2 horizontal for looking only shorter frequencies in order to detect or separate 2/FL problems. I mean, you need, when you use vibration, you need to set 2 different Fmax configuration, but using ultrasound, you don't need to use that. You only need to set and follow this point and this another point next to the bearing. And if you keep tracking the inspection route, you can modify whether you can get the best signal. As you see, better if you use the load of sound of the bearing. I mean, in the lower range, about this, the 44-degree sector. If you try to inspect on the vertical line, maybe you are going to diminish the amplitude of the signal. Anyway, when you are inspecting an electric sound, there is no a general rule. Maybe you can take the inspection here in the middle and get a better signal. As we were talking, what about if we have this problem in the middle of the rotor? It's probably that we can get the higher signal here. But for general inspections, begin using this 1 and 2 points. Looking the configuration about using 25 kilohertz. Right? Any more question? 450 HPs y 4160 volts. It's a big machine.
He asked about the module capacity, which is 450 HP.
Okay. If no any question, ladies and gentlemen, thanks in advance. Okay. Okay.
Can I ask? So you have a very extensive vibration program, right?
That's right.
And you started monitoring the motor using ultrasound on the bearings. you then stumble on this spectrum, which because you are vibration specialist, so you notice something is odd. Is that how it came about? That's why you're taking the two ends of the motor bearing, and this, this is not a bearing problem, but it's something else. Now, would you be taking readings from the body of the motor instead of just taking from the bearing? Would you be doing this, or would you advise people to do this?
In this case, no, because when I detected this failure was on this point, and in this point I got the best signal. You can see on the spectra, the spectral is very clear. And I decided not to move the point of inspection. But if you have any doubts, you are free to make the inspection around the machine. But here another tip is to use the ends, the bearings, because they are the support. Finally, the reaction forces are going to be reflected on the bearings. Yeah, any force, mechanical or electrical. Yes.
Okay, understand.
Thanks. One more question, yeah, over there.
You're like a rock star, Carlos.
You say you took your readings at 25 kilohertz. Did you see any difference between 30 kilohertz and 25 kilohertz, or did you even try it at 30 kilohertz?
About the frequencies?
Yeah.
Yeah. I decided to use 25. 25 is better, like for beginning, but you are free to load to 20 or increase no more than 30. But I recommend to begin your inspection with 25. Also, when you are inspecting, you have your headphones. You can try to dial and get the better signal. Yes, but if you are going to set that frequency, use them for getting this problem. So don't try to get back again or another guy and set another frequency, because they are going to mismatch information.
Anybody else? Now we clap.